All right, so let's get started. So today we will continue to talk about retransmission protocols. So we talked about stop and wait last time. So we will step into something called go back N. So that will be the first hour of this 2-hour lecture, right? It's 2 times 45 minutes. And the second 45 minutes would be the first of these guest lectures on different applications in ICT. So we will have 4 in total, or 3 guest lectures, and I will give 1 also. And then after that, you can select. You should select one of those for your part 3 of the project. Okay, so these guest lectures are sort of input to your choice, and also some basic material that you can start with when it comes to solving the part 3 of the project. So these guest lectures are not only to widen your horizons and learn about these applications, it also has an implication on your selection of projects, and therefore also on passing the course and whatnot. Okay, so if we continue here start, we talked about retransmission protocols, and the idea with retransmission protocols is that to provide a service that delivers service data units, and it should be delivered error-free, without duplication, and in order. And this is of course no problem if we have a reliable layer below us, but we will assume then that the layer below us is not reliable, that it could lose packets and so forth. So the idea here is that anyways try to deliver a service upwards which is better than the service that we have below us. So that's our goal here. So the key components for this are error detection mechanisms, use parity check codes, internet checksums, or CRCs, or some other error detection codes. We use sequence numbers to keep track of data units so that we don't deliver them out of order or with duplication, or lose them. We have timeout mechanisms, and this is because otherwise the protocol can get stuck waiting for, say, an acknowledgement that will never arrive. So we need timeout, and then we need these special packets called acknowledgements that the transmitter, or rather the receiver, sends these acknowledgements to the transmitter in order to acknowledge that some packets have been received. So these are the components. So the stop and wait main principle is very simple. So the transmitter sends packets or frames. I will use packet and frame as the same. It has no particular meaning. So let's go with frame. So it will send frames, the transmitter, with a single service data unit, with a sequence number and some error detection bits. And then some other header information perhaps. But these are the ones which are important for the stop and wait protocol. And then it will retransmit if the timeout expires. So when the frame is transmitted, a timer is started, and if that timer expires, then we retransmit the frame with the exact same content. And then it moves on to send the next service data unit in a sequence of those if an error-free acknowledgement is received with the correct sequence number. Acknowledgements which are received with errors are just thrown away, and if it has the wrong sequence number, it's also ignored. Okay. And then the receiver, what it does is it accepts error-free frames with the correct sequence number and then send an acknowledgement to the receiver. Frames with are errors in it, just toss them away, do nothing. Frames with the wrong sequence number can trigger a retransmission of the previous acknowledgement. Okay. Erroneous frames are never trusted, so we never work on those. We just take the safe thing to do is just to throw them away. And this is sort of like a general rule. Never trust anything in a frame where there are bit errors in it. If you can trust the frame content, but the content is somehow semantically wrong from the protocol point of view, you can do something about that. And in stop and wait, what it does is that it transmits the previous act that we have sent, because this could be an indication of a lost acknowledgement. Okay, so that's stop and wait. So is stop and wait any good? And we will now make some type of analysis of this. And we see that, yes, indeed, it's very good in certain scenarios and it's very bad in other scenarios. So let's try to pinpoint where it's good and where it's not good. And in the situations where it's not good, can we do something smarter? And that will bring us into this go back N protocols. So what we will talk about is efficiency of stop and wait. So of course we want high efficiency, but what do we mean by that? Well, it will just bear with me and it will become clear. But we start by drawing a time diagram here, where we have time on this axis, and here we have the transmitter. And the transmitter will do certain things in certain orders in order to deliver the frame. And then we have the receiver timeline here. Okay. So the first thing that happens when we do a transmission is that we start the transmission of the first bit of the frame at some point in time. And then we keep on transmitting this frame until it has expired, where we have transmitted all bits. So here's the transmission of the first bit, here's the transmission of the last bit, where we transmit them. Then it goes over the channel, which has, you know, some type of delay. So at some point in time, the first bit will arrive at the receiver side, and at some point the last bit will arrive. And the difference between the starting times here is the propagation delay. So this is the propagation delay, and let's denote this by the variable tprop. Okay, the time it takes to transmit the frame, let's call that TF. So this is the frame duration. So what's going to happen now at the receiver side when it has received the frame? Well, at this point in time, it has received the entire frame, so it will check the CRC or the error detection and whatnot. And then, depending on if it's an error or not, it will take certain actions. So let's assume that everything is okay now. So the frame has been received and it's correct, it has the right sequence number. Then the receiver will answer this by sending an acknowledgement back to the transmitter. But it will take some time before, you know, doing all this processing, checking for errors and, you know, deciding what to do. Assemble an acknowledgement frame with the right sequence number, and then start to transmit that. So there will be some, let's call it processing time here, tpros. So at this point in time, the receiver is ready to transmit back an acknowledgement for the frame it just received. So it will start to send it like this. And typically the acknowledgements are shorter than the information frame. So this is an information frame which contains an SDU. So this is the data that we actually want to transmit. And then we send back an acknowledgement frame here. So this is the ACK frame, like this. Okay, and the time the duration of the ACK frame, let's call it TA, like this. You know, typically shorter than the frame duration. Then it will be the transmission of the acknowledgement will go over the channel, will experience some propagation delay. So there is a propagation delay here before to denote the time where the last bit of the acknowledgement frame has arrived. And now the transmitter here can do some processing to check whether this acknowledgement is error-free and whether it has the right sequence number. And if it does, which we assume here, it is now ready to take on the transmission of the next frame. So here we have some processing time again. Okay, so these are the relevant variables that we need to play with here. We have propagation delay, frame duration, processing time, duration of the acknowledgement frame, some propagation time, and some processing time at the receiver side. And the time from when we initialize the transmission of the service data unit until the transmitter is sure that this has been delivered, this is called the turnaround time or reaction time. So the time from beginning to end of the transmission of one service data unit is called then T0, turnaround time. Or it's also known as reaction time. Okay, so this is the time it takes to deliver a service data unit from the beginning to the end, from the perspective of the transmitter, right? The transmitter is busy from this time to this time. It will be in the blocking state and not accept new service data units from above. At this point in time, it goes into the ready state, is now available for transmission of a new service data unit. Okay. So then we can then calculate what is the data rate of such a system. Right? We have a number of bits, useful bits in the service data unit in this information frame that are delivered, and it takes T0 seconds to deliver this. So the data rate is simply the number of bits, useful payload bits in the service data unit, divided by the time it takes to deliver that. You know, just divide these two numbers and we get the data rate. Any questions so far? Okay. So this timing diagram is quite important, so that's why I took some time in developing it. Right? So we will see this in a few lectures to come in different variations. Okay. Okay, so suppose the information frame contains NF bits. Okay, so there is NF bits here in the information frame. Some of these are payload bits and some of them are just overhead bits, sequence numbers, addresses, headers, and so forth. So out of these NF bits, NO bits are overhead. So, you know, check bits, addresses, header, other header information. Right? So then the service data unit size, which is the payload bits, that is the total number of bits in the frame, and then we just subtract off the overhead bits, right? So out of these NF bits, NF and subtract off the overhead bits are useful bits or payload bits. Okay, now suppose the layer below the stop and wait layer has data rate r bit per second. Okay. So remember now we're working with protocol layers. So if we are the layer that we implement this stop and wait, we get data from above and then we send it down. We assemble the protocol data unit, okay, the information frame, which encapsulates the service data unit that we get above, and then we have headers and whatnot, and then we push it down to the layer below, which is actually responsible for transmitting this. Now, suppose the layer below has a data rate of r bits per second, okay? Then we can calculate what NF and TF, we can calculate TF from NF, okay? So how can we find TF? Here. What would TF be? We have NF bits we want to transmit, and we have a data rate of r bits per second. It is not rocket science. Super, right. NF is the total number of bits we want to transmit, and we transmit with r bits per second. So this, dimension analysis, if nothing else, is the foundation for all scientific knowledge, right? If you know the units, you can construct the equations. Okay, so TF is NF divided by R. So of course, the more bits we have, the longer it takes to transmit them. The higher the data rate is, the quicker it goes to transmit these. Okay. And likewise, the time it takes to transmit the acknowledgement, which has NA bits in it, is NA divided by R. Okay. So this propagation time is somehow the distance divided by the propagation speed. Okay. So if this is over, in the simplest case where we only have, say, a cable or fiber optic cable or something like this. So in a fiber optic cable, what is the propagation speed, you think? So in a fiber we transmit light. Okay, so what will be the propagation speed, you think?
The speed of light.
Yeah, one would think. But in the fiber it goes significantly slower, so about 2/3 of the speed of light. But it's still quick, right? So the propagation speed could be negligible in sometimes, but it could also be significant if it's an Atlantic cable or something like this. It could be significant. So anyways, in the simplest case is something like this. It's something we cannot do much about. It's something which is given to us by the topology and the transmission medium. So we will think of this as something that we cannot control. It's something that's given to us. Okay. And the processing time here, it's something that we can control in a way. We can have faster hardware, we can have smarter algorithms and so forth. But for the time being, we will just assume that this is something which we cannot control either. We have a network, it has some hardware in it, the processing time is what it is. Okay, so now we can actually assemble what the reaction time or the turnaround time is in terms of all of these parameters. So let's do that. So the reaction time is what? Well, we just add here. We have two propagation delays. We have two processing delays. We have a TF and a TA. So it's 2 times Tprop plus Tpros plus TF and TA like this. Okay. And we just calculated what TF and TA is in terms of the size of the information frame in number of bits and the size of the acknowledgement frame in bits. Okay. Okay. So now the data rate experienced by the layer above the ARQ stop and wait layer. So what is that? Okay. So remember now, we're in a protocol layer. We're stop and wait. We use the layer below it. It has R bits per second. What is the data rate we deliver up? The layer above us, what data rate will it think we are delivering?
Maximum the same.
Pardon me? The maximum the same. It cannot be more than that. But now we actually know, since we know T0, how long it takes to deliver a frame, and we know how many information bits there is in the service data unit that we get above, we can calculate the data rate by just taking the number of bits we get from above and divide through the time it takes for us to deliver that. That will be the data rate that the layer above us will experience, right? And as you correctly pointed out, it can never be bigger than what we got from below. Okay, so sometimes we use a subscript here, effective. So this is what effectively they will see above. And we put up a 0 here also for notation, meaning that there are no errors in the frames or in the acts. So this is the best we can hope for. And it turns out that then this is NF minus NO divided by T0. Okay. So this is the number of bits in the service data unit that we got from above. This is the time it takes to deliver this. And then we can simply do a little bit of algebra, and we can write this as R 1 minus NO divided by NF 1 plus NA divided by NF plus R 2 T prop plus T pros divided by NF. The steps from here to here is just to replace NF and T0 with the things that we have done. So it is not difficult to show this. Okay, so this is the data rate that we got from below. Okay, and we know that we cannot deliver a data rate which is higher than this. So this factor here is something which is less than 1. So this is less or equal to 1. Obviously, we would like this to be as close to 1 as possible. And what can we see that is stopping us from this being 1? Well, first of all, we have a penalty here, right? There is a subtraction in the denominator here. And we see that we have a penalty of 2 sorts down here. This penalty and this penalty. If we can make everything within the boxes here equal to 0, we get 1 divided by 1, which is the best we can hope for. Okay. So what are the losses we make? Well, the first one is NO, the overhead bits, divided by the total number of bits in the frame. So this is loss due to overhead bits. Okay. Basically what it says is that we should not have so many bits in the header compared to the number of bits in the frame. Okay. Makes sense. Okay. this thing here is NA divided by NF. So this is the overhead because we have to send an acknowledgement frame back, right? It will take some time to do this, and that will, increase the turnaround time. So we would like NA, the number of bits in the acknowledgement, to be small compared to the frame. Okay. This is also some type of overhead if you think about it. Okay. So this is loss due to ACK frame, or ACK bits if you like. Okay. Okay, so here, however, we have something which is an interesting factor, and this turns out to be the crucial thing for determining the efficiency of stop and wait. Whether stop and wait is good or bad, it's this term. Okay. So what do we have here? Well, first of all, we have the data rate, and then multiplied with the propagation time plus the processing time. Okay, and multiplied by 2. And then we have that divided by NF. So this one will be a large number, which is bad, right? Because it's in the denominator. So we would like this to be small, but you see it will be large, surprisingly, when R is large. Okay? The higher the data rate is below, the worse our efficiency will be. Interesting. Right? It's sort of counterintuitive. But you see, increasing R here will increase this term, will increase the denominator, which will make our data rate, our efficiency to go down. Now, since we have R here also, the data rate will increase, but the efficiency will go down. Okay. So increasing R will hurt efficiency. Interesting. What else will hurt efficiency? Well, if we have a long propagation delay or processing delay, that will also hurt things. Okay. But we can counteract that by increasing the frame duration. But again, the frame duration is somehow limited to what we get from above, the number of payload bits we get. So we can't do so much about that either. Okay. So, anyways, this is known as the loss due to the delay bandwidth product. Okay, so the delay bandwidth product pops up quite frequently, and it's a really bad name, but it's what history has dictated that we should use. So delay somehow, we can get that by see that it has T-prop plus G-pros. That's some type of delay. Bandwidth in this case is referring to the data rate of the layer below it. Sometimes computer science people talk about the bandwidth of a channel, and what they mean is the number of bits per second can be transmitted over that channel or that link. And we see that everything is also here normalized with the frame size. Okay, so if one should say something, it should be the normalized delay bandwidth product. But typically this normalized is left out of the terminology. So we see that the interpretation of this delay bandwidth product is we can make a graph like this where we look at the channel that we have below us as a pipe where we put in frames. We put in frames with a certain in this. And okay, so we can think of this as the pipe model where the width of the pipe is the data rate. So the layer below us provides us with the data pipe, and the width of the pipe is the data rate, and the length of the pipe is 2 times the T-pros plus T-prop. Then the delay bandwidth product is NF divided by R is TF. Okay, so somewhere here we can have the information frame which has a duration TF. And then the delay bandwidth product is how many TFs, how many frames can we fit into this data pipe at the same time. Okay. And as it turns out, the killer for stop and wait is that if we have a very wide and long pipe, we are occupying only a small piece of that pipe when we are transmitting our frame. Then stop and wait is bad. Stop and wait is good when the frame duration is on the same order as the length of the pipe, or even longer. Then it's good. So how can we improve the efficiency of stop and wait? Well, basically what we would like to do is to transmit several frames in a burst and not sending them frame, wait for an acknowledgement, frame, wait for an acknowledgement. We want to say 1, 2, 3, 4, 5 frames maybe, and then wait for acknowledgements of them coming back. That will be a more efficient use of the data pipe here. And that is the fundamental idea of stop and wait. Go back in. So any questions before we go on to that? Okay. So these concepts about effective data rate and efficiency, or maybe I should call this, write this out also. So this is the efficiency. Okay, the efficiency will always be less than 1. Okay, and we want the efficiency to be high for our protocols. Okay, so ARQ, stop and wait is good sometimes and bad sometimes. And it's bad when the delay bandwidth product is high. Okay, so let's find a protocol which is good in this sense for this, and that is go back in. So go back in. So the main idea is to transmit multiple packets without waiting for an acknowledgement. Packets which have been transmitted must be stored locally in the protocol until we get acknowledgements for them. So then we need a buffer, and that buffer is called a window or a send window. So outstanding packets, these are packets which have been transmitted but not acknowledgement. They're called outstanding packets. So these outstanding packets are stored in a buffer called the send window. So this is a little bit of the terminology. Okay, so let's see how this send window works. So we will now adopt the notation from the book. We will assume that sequence numbers are m-bit numbers, which means that sequence numbers needs to be recycled. And this is because we don't want sequence numbers to take up many bits, essentially, because this is overhead. So everything that involves sequence number, all arithmetic will be modulo 2m. Okay, so if it's an 8-bit number, we will have, a 3-bit number will have the sequence number 0, 1, 2, up to 7, and then we restart from 0. So we recycle these sequence numbers. We would use something called sliding windows to keep track of the transmitted and received packets. So an example of such a sliding window is when we have a slider window which has size 8, which means that it can keep 8 packets in it. So it's a buffer with buffer size 8 packets. And if we use 4-bit sequence numbers, we know that we can enumerate the sequence numbers are 0 up to 15. Okay, so these are the sequence numbers we have. So we start with enumerating this, the packets 0, 1, 2, 3, 4, 5 up to 15, and then we restart and do 0, 1, 2, 3, and so forth. So here we can think of this as a time axis, and here we put in all the service data units we get from above. Okay. Some of these we haven't received yet, and some of them we have already transmitted and got acknowledgements on, and some of these are still outstanding. So to the left here, we have packets which have been sent and have been acknowledged. So these packets, the transmitter knows for sure has been delivered. Okay. Then the transmitter had transmitted this, what should we call it, these colored packets here, namely a packet with the sequence number 7, 8, and 9. These are still being in transmission. They have been transmitted, but have not yet been acknowledged. So the receiver doesn't, sorry, the transmitter does not know the fate of these packets. They are under transmission, have not yet been acknowledged. These are the outstanding packets. Okay. And then there are future packets which have not yet been delivered to us from the layer above. Okay. And these are packets, packets which are not stored. These packets are the packets which are stored. And these are space to store future packets which are currently empty. Okay. So these are from here to here, these are packets that could be, empty spaces in our buffer, our send window. And the total number of packets we can have in the send window is the size. And in this we have space for eight of these. Size 8. Okay. Now we have 2 pointers. One pointer which is pointing to the oldest outstanding packet, and that's called SF. We have another pointer, SN, which points to the next available slot in our buffer. So this is where the next empty slot is. We can also think of SN as being the next packet to send, but we have not yet received it from the upper layer. Okay. Any questions so far? So this is terminology. I encourage you to look at this slide to figure out what are the basic elements of a window, and what is the meaning of these pointers and so forth, and what is the size and so forth, because we will use this heavily as we go along. Okay. Now, if the whole send window is empty, then we don't have any outstanding packets. But in that case, we put SF equal to SN. So when SF is equal to SN, that indicates that there are no outstanding packets. That means that the send window is completely empty. We have nothing stored in it. Okay. So that's the initialization of it. Okay. So how do we fill up the send window? Well, we fill up send windows when we get data from the layer above. Okay. So packets will have sequence numbers according to the send window. So when we get a packet from above, from the upper layer, and if there is space to store it, then the transmitter accepts this. I mean, the protocol accepts it from the layer above. So we create a new packet then with a new sequence number, and the sequence number of the newly arrived packet will be SN, because SN is pointing at the first available empty slot in our send window. And then we will increment SN, so move that to the right. So when we get a new packet, we increment SN, so we increase that by 1, and we pop in the new packet here. Okay. And this packet, which we just got, will have the sequence number that was SN before we do the incrementation. So it will have number 0. Okay. And the next packet we will have number 1, and then we increment SN like this. So filling up the window is essentially to put in new packets at the point where SN is currently pointing, and then move SN to the one step to the right. And of course, when we have filled up the entire window, we cannot accept any more data from above, and then we block the upper layer. Okay, any questions? No? Okay, so we continue then. So a little bit about ACKs now, how to enumerate them and to do something called window sliding. So the transmitter will it's not the transmitter that sends ACK packets, it's the receiver. Sorry about that, that's a typo. So the receiver will, so the receiver will send ACK packets, and to acknowledge that he has received an error-free frame. Okay, and these ACK packets will include an acknowledgement number, this acknowledgement number, and let's call that ACK-no. Okay, so this can be interpreted by the receiver in different ways. So an ACK with ACK-no can, depending on the protocol, acknowledge one or several frames. It can acknowledge the packet which has a sequence number which is ACK-no -1, which is what we will actually use most of this terminology. Or it can acknowledge all packets with sequence number ACK-no. It can acknowledge the packet with the sequence number ACK-no, exactly that. Or all packets with sequence number less than ACK-no. And this is called cumulative ACKs. So we would use either this one or this one. Actually, we will use all three of them, but today we will use this one. Okay. So depending on the protocol, we need to make the proper interpretation of the acknowledgement number. That's my main point at this time. Now, the state variable SF, which is the oldest outstanding packet, is then updated when acknowledgements arrive. Okay. So when SF increases, we say that the send window slides. So when SF increases, we say that the send window slides. And that's easiest to show in an example. So let's do that. Okay. So if we use cumulative acknowledgement, and the send window looks something like this, and now an acknowledgement arrive, and it has ACK-no 9, and we use cumulative acknowledgement. That means that if I receive ACK-no 9, I know that all packets with sequence number less than 9 has been received. So 8 and 7 has been received in this case. So me as a transmitter say, okay, 7 and 8 has been successfully received. Okay, so I don't need to store them anymore. So I basically just delete them. Or another way to say is that I move SF, I increment SF to be equal to ACK-no, and then release these two spaces in the send window, which means that I can now store 2 new packets at the end of the send window. So the send window sort of slides to the right. Okay, so that's why it's called sliding window. So any questions on that process? No? Okay. So at the transmitter side, we have a window which has some outstanding packets. When we get an acknowledgement, we know that some of these outstanding packets, possibly at least, have been received correctly, and therefore we don't need to store them anymore. So then we just update SF to point at the oldest outstanding packet, always. And that causes the window to slide sometimes. Now, if we use a non-accumulative ACK, however, we don't always slide the window. So in this case, if ACK-no is 9 and we use non-cumulative ACK, that only means that 9 has been received. But me as a transmitter, I don't know the fate of 7 yet. Since 7 is still outstanding, I don't know if this has been received or not. I have no way of sliding the window because I need SF to point. I need to store 7 here, even though I know that 9 has been received. So the only way to slide the window is if I get 7 acknowledged and then 8 acknowledged. And when I get 8 acknowledged, I know that 9 has already been, and then I can slide 2 steps. Okay? Can I steal 5? No, I cannot. Okay, so I think we will stop here and then continue. We'll go back and at the next time we talk about this when we don't have a guest lecture. But the important things today was how to calculate the efficiency and the interpretation of the delay bandwidth product, the notion about efficiency, okay, And then we talked about these sliding windows. And so if you can understand the sliding windows, these two pointers at the transmitter side, SF and SN, and the various types of sliding we can do, then you should be in good shape for understanding go back N, which is the next big topic here in the course. And then we can calculate these efficiencies. We will calculate them for other protocols also to see whether they're good or bad. Right. Okay, but let's take 15 minutes and then we will have a guest lecture by Jimmy Enberg, who I will present when he comes here.